Good morning, everyone. Today we are going to talk about the phase transformation part 2. And last time we talked about the part 1 for phase transformation, and I talked a lot about these important concepts, and I hope you guys understand all these concepts very, very clearly. As I said, phase diagram and phase transformation, this is two most important topics in material science, especially for this class. The reason is that I want you guys to know and how well we can change the phases and how to read these phase diagrams. And so, without further ado, I'm going to continue our today's talk. And today's objective is that we are going to learn isothermal transformation diagrams. And as the name suggests, it means that something, whenever you see ISO, it means something is the same. Isothermal here means that the temperature is maintained constant when we cool the temperature, cool the specimen, cool the material, and we hold the temperature constant. And then we are going to talk about this one in detail. And transformations and undercooling. And so here, this is the phase diagram this um, of this iron and iron cementite, or this is an iron carbon phase diagram. And for transformation to occur, and eutectic transfer, okay, for eutectic transfer, eutectic transfer means that and if we lower the temperature, the phase is changing from one single solid phase to two solid phases. And for in our phase diagram, it means that we have austenite at this temperature, and also for this combination, if we cool it, and we will have alpha, which has very, very um, small carbon composition, and also this is cementite, which has a relatively high carbon composition. And so you can see we go down here. And so this is must cool to below 727 degrees C. So this is a eutectoid temperature. We must cool it and below this temperature in order to have this is alpha ferrite and this is cementite. So this is called undercooling. And so I hope you guys understand this phase diagram very, very clearly. In our previous class sessions, I talk about this one um, several times. As I said, phase diagram is the most important topic in the material science, and this carbon, iron and carbon phase diagram is the most important one in all the phase diagrams we have learned. Why? Because the iron carbon phase diagram means that we are talking about steels and also this cast iron. So these two categories of materials are the most commonly used in industrial applications, not just in US, but almost in and across the world. So that's the reason I cannot emphasize how important this phase diagram is. Any questions regarding this slide? No question. We'll take a look at this one, this temperature, this slide. So this temperature dependence for iron carbon alloy of eutectoid composition. And so you can see this is the time, the second. So this is the percent, and this is perlite. Percent perlite is alpha plus this is cementite. Cementite is Fe3C. So you can see the different temperature, and we can have different time for the completion of this transformation from this austenite to this ferrite and um, cementite. So these observations here, temperature plays an important role in the area of austenite to perlite transformation. And let me ask you a question. Right? I told you already. And what is a pearlite? And pearlite is a combination of ferrite and cementite. I should know that. And for each curve of these three curves, data were collected after rapidly cooling a specimen composed of 100% austenite to the temperature indicated, and which was maintained constant throughout the course of reaction. Right, so this is, you should know, this is the observations for this diagram. Any questions regarding this slide? No question. Then we move on to the next slide. So temperature dependence for iron carbon alloy of eutectoid carbonation. Now we talk about this carbonation here. So this first figure shows percent of austenite transformed to pearlite from 0 to 100%. And here this is the time. Okay, this is the time. After some time, the transformation begins and go through this 50%, and then go here. So this is the transformation, the point at which the transformation ends. And correspondingly, and for this is time and also temperature, and we want to see this is combination here. So this austenite, okay, at the very beginning, all the austenite, there's two curves here. So this curve is the begin curve, and the begin curve means that austenite, 100% austenite. So this curve is end curve. This is a completion curve, and so it means that after you cross this curve out, we cross this curve. That means we have 100% of pearlite. Austenite disappears. So this is two curves here. So this is a 50% completion curve. As you can see, this austenite stable eutectoid temperature here. So here you can see at the very beginning at this temperature, at the very beginning, and we have it starts, the next starts, then after some time, and we achieve 50% of pearlite and 50% of austenite. And then as the time goes, finally at this point, and we have achieved this 100% of pearlite, which is the combination of alpha plus and cementite. Any questions regarding this slide? Okay, no question. We move on to next slide. Uh, so temperature dependence for iron carbon alloy of eutectoid combination. The particular plot is valid only for iron carbon alloy of eutectoid combination. So that is, you should know that that is for the eutectoid combination. For other combinations, the curves will have different configurations. That means we have different curves. And these plots are accurate only for transformation in which the temperature of the alloy is held constant throughout the duration of reaction. In this sense, it is called isothermal. And so this is called isothermal transformation diagram. And you lower down the temperature, and then at this lower temperature, and you just hold this temperature constant. And so this is called isothermal transformation diagram. Any question regarding this slide? Now we talk about for this iron carbon alloy of eutectoid combination here. And so you can see for eutectoid iron carbon with superimposed as a thermal heat treatment curve. And we can see here, okay, we go down, lower the temperature, and then here, okay, and all this in this area, and we have this austenite, and so this is means we have 1, 2, 3, 4, and without loss of generality for this one, and we have 4 austenite grains, these grain boundaries. This I just show you example. For this is the circle. Actually, the circle has many these gamma austenite grains. You should understand that. At the time, uh, as the transformation begins, occurs starting from C here, and will disappoint, and we will, and you can see this microstructure, and so within this is a these gamma grains, and we will have this kind of the things. So this kind of lamella, and this lamella is the alpha ferrite, and this is the cementite. So this is um, light 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 the bands, and they are alpha ferrite. The darker bands, and they are this is cementite. And so you can see, and we have as the time out this transformation occurs, and gradually we will have lamellar that is growing within this gamma domain until this transformation finishes. After this transformation finishes, you can see all this gamma becomes this lamella of alpha ferrite and cementite. You can see still we have boundary conditions here, green boundaries here. So this is lamella, and this is different lamella, and they have different orientation. And so this is the you can see here. Okay, so this is alpha ferrite. This is the cementite. Here is a fine pearlite, and here is a coarse pearlite. Okay, so this is a coarse pearlite. Coarse pearlite means the green boundary is um, the grains are bigger. The fine pearlite means the grains are smaller. And fine pearlite, because the grains are smaller, and we based on what we have learned, and reducing grain size, and we can strengthen the material. So as a result, fine pearlite is strong and hard. Uh, the coarse pearlite is kind of soft and is not very strong. So this line denotes that a transformation is occurring. So this is the austenite to pearlite transformation. And any questions regarding this slide? Okay, so my bottom line is that if I give you this kind of the phase diagram, and if I can ask you to use your own words to explain on how this phase transformation is carried out here, and so you should be able to use your own language to tell people um, on how what happens here. Okay, so no question. We move on to next slide. Next slide. So this is the iron cementite and eutectoid transformation. The transformation of austenite to pearlite, as I said, pearlite is a combination of alpha ferrite and this cementite. And so here is a gamma, right? Here is a gamma here. And so here is changing now. Austenite, this green boundary. So here is a cementite, and this is a dark band, and this is a lighter band is a ferrite, and as this is a solid, the crystal grows, and it grow in this direction, and in this direction, because alpha ferrite and cementite, and they have very different combinations of C carbon, so there must be the gamma. We know gamma has another combination of C. So as the pearlite grows, and we must have diffusion of carbon. And so this is the you can see here. Okay, so um, when this is the pearlite grows, when this is the solidification grows here, not solidification, I'm sorry, this is the phase transformation grows. And so you can see these carbon atoms are going from this area, and to this is the darker area. And because darker area is a cementite, which has a higher carbon and composition. So this alpha is ferrite, has low carbon composition. So you can see, so this is more carbon atoms um, move to this is dark bands here. So carbon diffusion rates are high. Can you see? And if the carbon diffusion rates are high, and we have, and this is a coarse pearlite. If the carbon diffusion rates are low, and we have fine pearlite. So coarse pearlite are formed at a high temperature, as I showed you in the previous slide. At high temperature, relatively soft. Fine pearlite are formed at lower temperature, relatively hard. Any questions regarding this slide? So this is the schematic representation of this is a phase transformation about the diffusion of carbon atoms during phase transformation. And then we talk about this is a micrograph of these pearlites. So we have two megagraphs here. And so first one is the coarse pearlite. Okay, this is coarse pearlite. And here is the fine pearlite. And this fine pearlite. And this is shallow, this is light material here, and is alpha ferrite. And so this is dark material here. These dark lines, and they are um, cementite. Also here cementite here. You can see. So this one and this, they have different orientation. This must be this one grain, this is another grain. So this is the grain boundary. And they have different grain orientation. So here is a fine pearlite. You can see the fine pearlite here. And fine pearlite magnification is 3000. And fine pearlite here, you can see still the light area um, denote light areas denote the ferrite, the dark areas denote the cementite. This is a pearlite is a composition of alpha ferrite, and this is the alpha ferrite and this cementite and in lamellar form and layer alternation layers. Any questions regarding this slide? No question. Then we move on to next slide. So for 1.13 with percent of alloy, and so here this is the you can see. So this is pearlite, and A means austenite. Here is A plus this P pearlite and austenite. So this eutectoid temperature here, right? And so if we have this one and austenite, so you can see it, we can have I'm sorry, this is A, right? This is A austenite, and so this is also austenite. Uh, and then transformations involving non-eutectoid compositions. And the eutectic the composition is only a one and single composition. And what if we have these compositions that are different from eutectoid composition? And for example, here, so this if the composition is not here but in between this point and this point, and what do we call? We call if the combination is higher than eutectoid, and we call this hypereutectoid. And similarly, right, so for this is the combination that is lower than the eutectoid combination, and we call hypoeutectoid. So I told you these two concepts in our previous slides, and I hope you still remember these these two new concepts. And for here, right, so hypoeutectoid combination, we call pro-eutectoid cementite, and this is a pro-eutectoid cementite here, right? Because we will have this gamma there inside. I'm going to show you. And so we talked to you. I talked to you last time a little bit already. Excuse me. And so here is another the microstructure called bainite. And bainite is another iron and cementite transformation product. So bainite is elongated cementite particle in alpha ferrite matrix. So major body is the alpha ferrite. We have the cemented particles embedded in this matrix. It is diffusion controlled. As a thermal transfer diagram, and for C, 0 equals 0.70 with percent of carbon. You can see here, we go here, okay? and we will have, and here we have this pearlite. This is pearlite. But here is a demarcation line here. However, if the temperature you lower to is lower than this point, this nose, okay, we call it like this nose. So this is the bainite, pearlite and bainite. And so this is a new concept, and you should know this one very, very clearly. So this is a schematic representation, but here is a micrograph. We have here alpha ferrite is a major body, and then we have this is elongated and cemented. You can see this elongated and cemented particles. So just like composite, okay, alpha is a matrix. So FC 3 carbon, and this is embedded in the alpha ferrite matrix. So this is another microstructure called bainite. And this is another one, and called spheroidite. Spheroidite, as the name suggests, it is a circle instead of elongated one. Okay, so this is another microstructure. What is a spheroidite? I'll talk about these cementite particles within an alpha ferrite matrix. And formation requires diffusion, right? Requires diffusion because there's alpha and cementite, and these two guys have different carbon composition. And heat bainite, so this is bainite, or perlite at a temperature just below eutectoid for a long time. And heat bainite and perlite at a temperature just below eutectoid for a long time. And then you will have this spheroidite. The driving force, reduction of alpha ferrite and cemented interfacial area. And in physics and in physics, we have learned that, and also in our mechanical engineering courses, um, I always tell my students that any system in the universe, and they have the tendency to minimize the potential energy in order to maintain a more stable state. And so this is true for this system. Because we know that this is sphere circle and has the minimum energy. The circle, the ball, this is the we call sphere, and they have the minimum potential energy. Um, as a result here, so if you have the if you just hold this is a specimen for a long time, so this is a this is a heat, and will change, and this is a microstructure, and then will the elongated the particles will become the sphere. As I said, sphere has lower tension and lower surface energy. So in order for the system to minimize the potential energy, so this system will do this. I hope you understand. Okay, so you understand this. Every in the universe, any physical system or these even biological systems or these chemical systems, and they have the tendency to minimize the potential energy and to maintain a more stable state. And wide circle, and maybe you have already know that when you put some water on the surface, the water finally will take the form as a sphere instead of rectangular, instead of triangle. Do you guys know why? The reason is the same here as here. Okay, so the sphere has the minimum surface energy and have the surface energy to do that. So this is with that being said, and I hope you guys understand the driving force. Uh, if I ask you what's the driving force for the formation of spheroidite and from this bainite or this perlite, and you should be able to tell me the driving force is that the system tends to reduce the interfacial area between alpha ferrite and this cementite particle. You should know that. Okay, so this is um, in our quiz or exam. If you can answer questions this way, so insightful. In if you answer it so insightful, I will be very very happy. And then we talk about another one. This is martensite. Martensite is a non-equilibrium transformation. And so this martensite, this is another one. Okay, another you can see martensite means that we form gamma arsenide And austenite has the FCC, face-centered crystal structure, and to martensite. Martensite is body-centered, BCT, and it's another crystal structure. So here is the Fe atom sites. So this one, this is a potential carbon atom sites. So here is the martensite needles. So this is needles, very, very long, and they are martensite needles. The dark, the dark area, this light area is the austenite. Isothermal the transformation diagram. Here, okay, so here is the nodes. This is the begin curve, and this is the completion curve. So this is a 50% curve. And however, if your cooling rate is much higher, and so the cooling, the cooling curve does not touch any part of this transformation curves, and begin curve and this end curve. And so they will not form pearlite will not form bainite, and no spheroidite. And then you will go to the martensite directly. So finally, if you go here, and you will have the combination of martensite and this original, um, this is austenite. Original austenite, because the cooling temperature, the cooling rate is so high, and not all of these austenite can become martensite. Only part of the austenite become the martensite. However, there are remaining austenite. So these are from 100, 0%, 50%, and this 190%. And so you further go, and you will have more. This is martensite and less austenite. You can see gamma to martensite transformation is rapid. The cooling rate is very, very high. Because the cooling rate is very, very high, so the carbon atoms and almost does not have any time to diffuse. And so this is we can call this a diffusion lease. And so percent transfer depends only on the temperature and to which rapidly cooled. Only depends on your ending temperature here. Any questions so far? And for example, at this temperature you have 0%, and at this temperature you have 50% of martensite. At this temperature you have 90% of martensite. Questions so far? No question? And then we talk about martensite, the formation. Okay, gamma austenite, FCC, slow cooling, and we have alpha ferrite, and this is the cementite. And what do we call? We call this pearlite, right? And if we quench it, we will have martensite. We'll call this is called quenching. Martensite is a single phase and has body-centered tetragonal and body-centered tetragonal. This is another crystal structure. When we talk about the crystal structure, I emphasize four crystal structures. One is a simple crystal structure. Second is a BCC, body-centered crystal structure. The third one is FCC, a face-centered crystal structure. The fourth one is HCP, crystal structure. And for this, there are several other crystal structures. I did not talk about too much, all of them. And then you know that this is the BCT is another body-centered tetragonal. So diffusion leads transformation. And BCT, if this is a C0 is greater than 0.15% C, and BCT and has fewer slip planes, that means fewer slip systems, and as a result, it is harder, it's hard and brittle. Right? So this is because the slip systems, the more slip systems, the more slip system the material has, the more ductile this material, because this material will have more directions and to accommodate the plastic deformation instead of breakage immediately, directly. Questions regarding this slide? Okay, so this because the martensite is always very, very brittle and very, very hard. It cannot be used for the engineering applications. In order to use this, we need to temper it. And temper it means that we elevate the temperature and hold the temperature for a certain amount of time, and then we will have tempered the martensite. Tempered martensite, the hardness is reduced a little bit, but it is more ductile, so the tempered martensite can be used for engineering applications. The martensite itself cannot be used because it is extremely hard, extremely brittle. Any questions so far? I want you guys to know what's the difference between martensite and this tempered martensite, and how we get this martensite. We call this special process quenching. So this is the tempering, called tempering. So this is phase transformation of alloys. We just talked about the iron and iron cementite phase diagram, phase transformation. And what if we use some alloying elements, and what kind of effects the alloying elements can have on the phase transformation? So the experiments have shown that, right? So this is the chromium, nickel, molybdenum, silicon, and manganese, and they can retard the transformation from gamma to alpha ferrite and cementite reaction, and then retard the formation of pearlite and bainite. That means if we alloy these kind of elements in our iron carbon system, and we will have the this is the uh, this begin curve and end curve of phase transformation will be the postponed, will be pushed to the right. That means it will take a longer time. And as it here. Okay, so this is austenite, austenite plus ferrite, austenite. This is the ferrite plus this called this pearlite here. So this here is a bainite. Here is a bainite. This is martensite. You can see it is a changing, right? It is a changing.